of U is a sufficiently smooth nonlinear differential operator of order k. So first we need to define what is a linear space. Linear space is nothing but a linear span of n linearly independent functions over R. So here this Wn denotes the dimension of the invariant subspaces. So here, what is the invariant subspace? A finite dimensional linear space Wn is said to be invariant with respect to the differential operator f if f of Wn subset of Wn, that is f of u belongs to Wn for all u belongs to Wn. If the given differential operator f admits an invariant subspace, then there exist n functions psi1, psi2, psi(n) such that f of linear combination of the n linearly independent function, we can write this. But here we assume that invariance of space, that Wn is defined as the space of the solution of linear nth order ODE. So here another important thing is, here what is the invariant condition? Suppose if f admits the invariant subspace Wn, then invariant condition for the subspace Wn with respect to f takes the form, this form. Here another important thing is how to find the dimension of the invariant subspace. The dimension of the invariant subspace is depends on the order of the differential operator. So if a linear space Wn is invariant under a nonlinear differential operator f of order k, then maximum dimension of the invariant subspace is 2k plus 1. K is the order of the differential operator. So here the one important thing is the invariant subspace method allows nonlinear PDE into system of, that means the invariant subspace allows one to reduce nonlinear PDE into system of ODE. The obtained system of ODE may be solved by well-known methods. Suppose if Wn is an invariant under the differential operator f, then nonlinear PDE admits exact solution is in this form. That means a finite separable form, where this Aj of t satisfies the system of ordinary differential equation. Now I am coming to the convection reaction diffusion equation. Let us consider the well-known family of generalized convection reaction diffusion equation. This term denotes the diffusion, this term denotes the convection, and this term denotes the reaction term. The convection reaction diffusion equation can be classified into the convection, reaction, and diffusion equation. But how we can construct the complete classification of invariant subspaces and how we can derive the exact solution for the given equation. For example, the given equation can be written in this form. First, we need to define the linear space. The linear space is nothing but a solution space of the linear ordinary differential equation. But what about the dimension of the subspace? Because this dimension is the depends on the order of the differential operator. The given differential operator order is 2. So therefore, the maximal dimension is 5. The possible dimensions are 2, 3, 4, 5. So hence, first we consider the dimension n equal to 2. For example, I am considering the dimension of the invariant subspace is 2. For example, the two-dimensional trigonometric subspace is invariant under the cubic differential operator. That cubic means this A of u in this form, B of u, C of u. So here, because z bar of u in this form, but this satisfies the invariant condition. So therefore, we can say this space is a invariant under the cubic differential operator. But how we can find the invariance of space? That is very important. So here I am considering the first dimension n equal to 2. The differential operator g bar from W to W2. So W2 is nothing but a solution of the ordinary differential equation, where A0 and A1 are constant to be determined. The corresponding invariant condition can be written as in this form, but where g bar of u given differential operator. So if you are substituting this g bar of u into the equation 10, that equation reduces to this equation, but this equation gives the system of overdetermined equation. Solving the overdetermined equation, we can get complete classification of two-dimensional invariant subspaces. For example, the above equation gives that a1 equal to 0 and a of u this form, b of u equal to constant, and c of u is a cubic function. Thus, we obtain the invariant subspace, two-dimensional trigonometric subspace, from calculating from this ordinary differential equation. Therefore, we can write the exact solution u of x comma t equal to this form, where c1 of t and c2 of t are the unknown functions to be determined. Similarly, we can construct the two-dimensional polynomial subspace. The polynomial subspace is invariant under the cubic differential operator and quadratic differential operator, because A of u is this form, B of u, because this gives the G bar is a quadratic differential operator, this gives G bar is a cubic differential operator. So another one is here we can classify the invariant subspaces are polynomial, trigonometry, and exponential. So here first next one is exponential subspace type. So here two-dimensional exponential subspace. This is a type 1. This is a invariant under the three different quadratic differential operator. And the next two, this is a two cubic operator. That means this exponential subspace is invariant under the three different cubic quadratic operator. And this invariant subspace is invariant under the two cubic operator. So here the next type 2. So this invariant subspace is invariant under the quadratic differential operator. Suppose I am assuming arbitrary linear subspace that is invariant only under the linear differential operator. So here similarly we can construct the three-dimensional invariant subspaces W3. This is a polynomial subspace is invariant under the quadratic operator. Exponential subspace, three-dimensional exponential subspace is invariant under the quadratic operator. The trigonometric subspace, this is invariant under two different quadratic operators. So here one important thing is dimension of the invariant subspace is greater than or equal to 4, then this invariant this linear space is invariant only linear differential operator. So that means only already we know what we know, dimension of invariant subspace is less than or equal to 3. We obtain both linear and non-linear differential operator, the G bar of u, along with parametric restriction. The possible nonlinear differential operator with their corresponding invariant subspaces are already discussed. So dimension is greater than or equal to 4, then we are obtaining only linear differential operator. So here the linear differential operator I am considering, this admits the following invariant subspaces. For example, we can classify polynomial, exponential, and the combination of polynomial and exponential, and the trigonometry also. The last one is a more general invariant subspaces because it contains polynomial, exponential, and trigonometry. So here the dimension is not a problem only when we are facing the dimension of the invariant subspace if the given operator is a nonlinear. So if I am taking this operator k not equal to 0, then I am obtaining these invariant subspaces. Similarly, we can classify polynomial, exponential, and trigonometric subspaces. But here we calculated invariant subspaces. How to derive exact solution using the obtained invariant subspaces for convection, reaction, diffusion equation. In the here, I am considering convection, reaction, diffusion equation with power law nonlinearity. So I am assuming A of u in this form, B of u, and C of u. Then the given equation, CRD equation, that is convection, reaction, diffusion equation, reduces to this form. So this H bar admits one-dimensional exponential subspace. Here, the one-dimensional exponential subspace, easily we can verify the H bar satisfies the invariant condition. It is satisfied, then we can write the exact solution of form u of x comma t equal to a1 of t into e power ax. If you are substituting this 14 into the given equation, that reduces to ODE. So if you are solving this ODE, we get a1 of t this form. Then we can write the exact solution of the convection, reaction, diffusion equation with power law nonlinearity. So similarly, we can consider the two-dimensional exponential subspace, and the two-dimensional exponential subspace is invariant because this is already we calculated invariant under the quadratic differential operator because it satisfies the invariant condition because G bar of u again in W2. So then we look for the exact solution u of x comma t is this form where a1 of t and a2 of t satisfy the system of nonlinear ODEs. Then if you are solving this system of nonlinear ODEs, we obtain the exact solution in this form. So next one, similarly we can derive another exact solution using the two-dimensional exponential subspaces. For this case, we obtain this exact solution. Similarly, we can derive polynomial solution using the two-dimensional polynomial space. and a three-dimensional polynomial space. Here we would like to point out that when A of u equal to 1 and B of u equal to u and C of u equal to 0, then convection, reaction, diffusion equation becomes a Burger's equation. This Burger's equation admits a two-dimensional polynomial invariant subspace. Then we can write the exact solution in this form, where C1 and C2 are unknown functions to be determined. So similarly, we can derive the trigonometric solution. This is already we checked, this satisfies the invariant condition. Then we can write the exact solution in this form, where A1 of t and A2 of t satisfy the system of nonlinear ODEs, but the system of nonlinear ODEs may not be solvable in general. So therefore, I can take C naught equal to 0 and A1 of t equal to A2 of t, then we obtain the exact solution for the convection, reaction, diffusion equation along with some parametric restriction. So we get this exact solution. The geometrical representation is given. So next, the big important thing is, here, is this method applicable to initial value problem or not? Yes, this method is applicable to initial value problem. For example, consider the Fernberg-Witham equation. So this equation with the initial condition here I considered, by using the invariant subspace method, we can find the exact solution in this form. So because here this operator admits one-dimensional exponential subspace, so which then we can find the exact solution which satisfies the initial condition. So here, how we can extend this method to fractional partial differential equation, and why we need to study the fractional differential equation. In reality, a natural phenomena may depend not only the time incident, but also on the previous time history, which can be successfully modeled by using the theory of derivative and the integrals of arbitrary order. Fractional diffusion equation is this form, but this alpha ranges between 0 to 2. When alpha equal to 1, the given equation 25 becomes a classical diffusion equation. When alpha equal to 2, the equation 25 becomes a classical wave equation. 0 less than alpha less than 1, the equation 25 becomes a subdiffusion equation. It represents slow movements of particles. Alpha greater than 1, the equation 25 becomes a superdiffusion, fast movement of particle. For 1 less than alpha less than 2, the equation 25 studies the intermediate process between diffusion and wave behavior. Hence, we observe that fractional differential equation provides a tool to study both PDEs of parabolic and hyperbolic type process simultaneously. But the derivation of exact solution of fractional differential equation is not an easy task, because some properties of fractional derivatives are harder than the classical one. For example, the derivative of the product of two functions, that is Leibniz rule for arbitrary order. So here alpha is arbitrary order. When this is true, if alpha equal to 1, this is true, but this is not valid for arbitrary order. Similarly, the commutative property is not valid. So when this property is true, if either alpha 1 equal to alpha 2, or both alpha 1 and alpha 2 are integer, or either alpha 1 or alpha 2 are integer, then this property is true. Similarly, the semi-group property is also not true in general. So therefore, when this is true, if alpha 1 and alpha 2 are both are equal, or both are integer, or either alpha 1 or alpha 2 are integer, then this is equal. So the fractional PDEs are more complex than the classical PDE. For these reasons, there exists no well-defined analytical method analyze them systematically, because many classical methods we can't extend to fractional partial differential equation due to these properties. So here I am considering the following sixth order time fractional dispersive Boysensko equation. The operator f, this is a sixth order differential equation. So the order of the differential operator is 6. The possible dimension, invariant subspace dimension, is maximum dimension is 13. First we consider n equal to 2. So here, if I am considering the dimension of the invariant subspace 2, the differential operator admits two-dimensional subspace, that is a two-dimensional trigonometric subspace, if beta equal to 4 into gamma minus 4 mu, because it satisfies the invariant condition, and then we can write the exact solution in this form: u of x comma t equal to c2 of t cos x plus c3 of t sin x, where because here also the invariant subspace method allows one to reduce time fractional PDE into system of fractional ODEs. Here we obtain where C2 of t and C3 of t satisfy this system of ODEs. First, I am considering the integer case. Then we get the exact solution in this form. Now I am considering non-integer case. Then the above system of fractional ODEs can be solved through the Laplace transformation technique. C2 of t, C2 of t and C3 of t we obtained in this form. But what is this? This is a Mittag-Leffler function. Mittag-Leffler function is a generalization of exponential function, because we know exponential function naturally occurs as the solution of the differential equation. Here, Mittag-Leffler function naturally occurs as the solution of the fractional differential equation. Here, then we can write the exact solution of the sixth order time fractional nonlinear dispersive Virchow equation in this form. This solution is valid for all alpha. Alpha belongs to 0, 1. Note that for alpha equal to 1, the equation 32 is exactly same as integer case. So similarly, we can consider the three-dimensional invariance of space. The operator F admits the three-dimensional three-dimensional trigonometric subspace if beta equal to 4 into gamma minus 4 mu, because it satisfies the invariant condition. Then we can write the exact solution in this form, where C1 of t and C2 of t, C3 of t satisfy the system of fractional ODEs. So next, I'm considering the time fractional reaction diffusion equation of second order. So here I'm considering only dimension 2. So here the dimensional 2, I got two different invariants of spaces. So here I'm considering the first case. Then we can find the exact solution for the integer case. Then we can find the exact solution for non-integer case. Here also note that for alpha equal to 1, equation 38 is exactly equal to equation 32. So here, actually here the systematic procedure here I'm not given, because due to the time. So here we can extend to time fractional delay partial differential equation also. Here I'm considering the delay diffusion equation with source term. So this h of u comma u bar is a operator. This is a order of the operator is 2. Then here this h of u comma u bar admits the two-dimensional invariant subspace, that is a trigonometric subspace. If this, that means this two-dimensional trigonometric subspace is invariant under the cubic operator, it satisfies the invariant condition, then we can write the exact solution of the delay diffusion equation with source term in this form, where a1 of t and a2 of t satisfy the system of ODEs. So here, under other applications, we can extend this method to two-coupled system of time fractional PDE and two-coupled system of time fractional PDE in higher dimension also. Here, I'm considering two-coupled system of time fractional PDE. This is a more general form. Here, this operator G1 order is K1 and G2 order is K2. So here also we can use the similar process. So here, first we need to define the linear space. So when we can say the linear spaces are called invariant under the vector differential operator, that is a component G1 and the second operator G2 that satisfies this condition, then we can say the linear space is invariant under the given given differential operator. So if the operator admits invariant subspace, then we can write in this form. Here also, the invariant subspace method allows a two-coupled system of time fractional PDE reduces to fractional ODEs. So if the linear spaces are invariant with respect to the fractional differential operator, then the two-coupled system of PDE admits this solution form. So where this coefficient satisfy the system of fractional ODEs. For example, I'm considering two-coupled time fractional nonlinear diffusion equation, but this diffusion equation admits more than 10 invariant subspaces, but here I can't present. So here I'm taking only one invariant subspaces. So here this invariant subspace gives the exact solution for integer case and the exact solution for non-integer case. So here, if you are taking alpha equal to 1, then the exact solution 44 is exactly equal to 43. So similarly, we can extend this method coupled system of time fractional PDEs in 1 plus 2 dimensional, because here I'm considering the space variable x and y, time variable is t. This is a arbitrary order because fractional time fractional PDEs. So here Here also we can use the similar process, and when we can say the differential operator n1 and n2 is said to admit the invariant subspace W if satisfied this condition, that here then if it is invariant under the differential operator, then we can write this form. So here also the time fractional coupled PD in higher dimension that reduces to system of fractional ODEs. The ODE may be solved by well-known analytical method. So here also we can assume the linear spaces is defined as the solution of the following linear ODEs. Here we can write two type of invariant subspaces, type 1 and type 2. So here we can write this dimension is different. Because this dimension is different, here we are writing separable form, but here we are writing the function alone, because here m1 n1 dimension, the first linear space, here m1 plus n1. So here we can write two type of invariant subspaces. So similarly, we can extend this method to scalar and coupled PDs in higher dimension with delay and without delay. The invariant subspace method is also called a generalized separation of variable. In this talk, we have explicitly presented the convection reaction diffusion equation admits more than one invariant subspaces in different dimensions, which in turn helps to derive more than one different exact solution. The main important is the invariant subspace method allows one to reduce nonlinear PDE into system of ODE. The obtained reduced system of ODE may be solved by the well-known analytical method. The obtained exact solution can be expressed in terms of polynomial, exponential, and trigonometric functions. So this study shows that invariant subspace methods provides a very effective and powerful mathematical tool to derive exact solution for integer or arbitrary order scalar and coupled system of fractional PDEs. So here references, this first book is a very nice book for exact solution and invariant subspace of nonlinear PDEs in mechanics and in physics. This paper, he discussed about the quadratic nonlinearity with invariant subspaces, and the Balyanan and Zurov used the invariant subspace method to nonlinear delay diffusion equation. And this my paper is this paper, because here I found new exact solution of generalized convection diffusion equation. And the another paper, this is a time space fractional coupled diffusion equation. So some other paper here I mentioned related to invariant subspace methods. So thank you so much. Any questions?
Yeah, thank you.
Thank you, sir. Thank you very much.
Prakash.
Yes,
It was a wonderful lecture. Yeah, so I really appreciate the way you have presented your work, and very involved lecture relating invariant subspaces, exact solutions, okay, and then giving applications to nonlinear partial differential equations. So it was a really wonderful, well planned. I really appreciate your presentation, and I think this will be helpful to the young generation, means other researchers who are working in this particular area. So very much thankful to you. And I now, some questions may be asked. Yeah, maybe if there are some questions, one may ask. If I hope that if there are no questions, then congratulations to Dr. P. Prakash.
Thank you very much, sir. Thank you. So I need to say a few words. I am very happy to receive A.M. Mattai Award. And first of all, I would like to thank Indian Mathematical Society. Also, I would like to thank Secretary of Indian Mathematical Society, President of Indian Mathematical Society, Academic Secretary of Indian Mathematical Society, and the VIT Organizing Committee. Also, finally, I would like to thank Professor A.M. Mattai. Thank you so much.
Yeah. Over to the...
Yes. So on behalf of the organizing committee of IMS 2020, I thank Dr. P. Prakash from Amrita Visvavidyabidam, Coimbatore, to deliver the A.M. Mathai Award lecture on the topic Invariant Subspaces and Exact Solution of Nonlinear Partial Differential Equations. I extend my sincere thanks to the chairperson, Professor B.N. Wapper. And over to Professor Rusikumar, sir.
Thank you, Dr. Sivaraj. I'd like to thank Professor Wapre sir and Prakash for a nice talk, and
Thank you, sir.
Wapre sir for chairing the session. I'd like to invite Professor Wapre sir to hand over the Mathai Award certificate to Professor Prakash.
Oh, it's my great pleasure to hand over the certificate to Dr. P. Prakash on behalf of the Indian Mathematical Society.
Thank you, sir. Thank you.
Yes, sir.
So thank you very much, sir. Thank you.
Certificate is handed over to Professor P. Prakash by handovering by Professor Wapre sir. This is A. Mathai Award for the year 2020. Congratulations.
Thank you, sir. Thank you. Thank you very much. I'm very happy.
Thank you. We are on time. The session is over now. Now we have the two parallel sessions. The important announcements to the participants. Please note that there are two important symposiums are scheduled between 10:45 to 1:15 p.m. today. The first symposium is Graph Theory and Combinatorics in honor of Professor S.S. Sirkande. So it is convener of the conference is Professor S. Sarad Sen, is the convener, is CMI Chennai, and Professor R. Balakrishnan, Professor Bhaskar, Professor M.K. Srinivasan, Professor Rajendra Paule. The eminent speakers are delivering talks in the symposium, Graph Theory and Combinatorics. Who are interested to join, all the participants are requested to, based on your interest area, either Graph Theory and Combinatorics, one symposium. Another symposium is Symposium on Biomechanics. So the speaker is Professor, the symposium is Biomechanics Symposium is organized by Professor B.V. Ratish Kumar, IIT Kanpur. The speakers are Professor G. Radhakrishnamacharya, Professor P.V.S.N. Murthy, Professor P. Muthu, Professor Meena. So I request all of you, please check your mail. We have sent a link, a separate link. This link is different. The symposium for graph theory link is different. The symposium for biomechanics link is different. We request all of you, please join. There are wonderful lectures are planned in symposium. Please join us. Exactly by 10:40. We are requested to join through 10:45 a.m. Over to Pish Chandra, sir. Sir, if you want to say any announcement.
No, I think everything is going nicely.
Yes, sir.
That's it.
Yes, sir.
Now you are the boss. You have to take care all the way.
Yes, sir. Yes, yes sir. Yes.
Only thing is that you could also say that honorarium.
Yes, sir. Honorarium. Yes, sir.
Certificate, and this will be sent by mail.
Yes. Sir.
Yeah, it should also be mentioned there that the prize will be sent later on.
Yes, sir. Yes, sir. We'll inform, sir. Afternoon,
the prize will be given later on.
Yes, sir.
Our prize will be mailed.
Yeah.
Yes, sir.
It is not like KBC that we are putting it and then it's going there.
But it's what we mentioned so that the speaker knows that he is getting the envelope also.
Yes. Yes. Thank you, sir. Shall we close? And I want to start the new link, sir.
Yeah, please.
I want to log in. So thank you, sir. I'm closing the session. Please join us the symposiums. Thank you. Thank you.